Assalamu alaikum everyone, I am Mahfuz Hassan and today I am going to talk about container orchestration with Kubernetes. We hear the word Kubernetes everywhere in modern tech. It can seem intimidating, complex and vast, but at its heart it's simply a tool to manage the chaos of distributed applications. Over the next few minutes, I am going to walk you through the core components, the brain, muscle, and the nervous system that make Kubernetes the industry standard for container orchestration. Let's dive in. Every operation needs a headquarter. In Kubernetes, we call it the control plane. Think of this as a brain of the cluster. It makes all the global decisions. It consists of four key components. The API server. This is the front door. Whether you typing a command or running a script, everything talks to the cluster through here. HCD. This is our memory. It's a highly available dataset that stores the state of entire cluster. The controller manager. This is a tireless worker. It constantly checks the state of the cluster and fixes it if something drifts away from what we want. The scheduler. It is a logistic manager. It looks at your new applications and decide exactly which machine has the resources to run them. If the control plane is the brain, the worker nodes are the muscle. This is where your actual applications live and run. On every single worker node, you have a agent called Kubelet. The Kubelet listens to orders from the control plane and ensure the containers running healthy inside their pods. Alongside it, we have a Kube-Proxy which handles the networking rules, ensure traffic get to the right place. As you can see in this diagram, these nodes work together to form a cluster where the actual work gets done. Now that we know where things run, let's look at what we are running. These are the essential building blocks. First, the pod. This is the atom, the smallest unit in Kubernetes. We don't deploy containers directly. We wrap them in a pod. However, we rarely manage pods manually. We use a deployment. This allows us to declare I want my app running, and the deployment handles update and scaling automatically. The thing which helps the deployment is ReplicaSet, which guarantees scalability. If you ask for 3 copies of your app, the ReplicaSet ensures that there are always exactly 3 running, even if one crashes. Applications aren't just code, they need configuration and secret. Kubernetes handle it elegantly. We use namespace to organize resources. Think of this as a virtual wall inside your cluster to separate different teams or environments. For setting, we use ConfigMap. This lets you change your app's configuration without rebuilding the whole image. And for sensitive data like passwords and SSH keys, we use secrets, which keeps that secure and separate from your application code. As we scale up, we need to expose our apps to the world and manage data. To manage external traffic, we use Ingress. This is like your smart receptionist. It handles HTTP routing, SSL termination, and makes sure that traffic gets to the right service. On the right, we have stateful sets. While deployment are great for stateless app, database need order and uniqueness. Stateful sets guarantee that your database pods start up in a specific order and keep their identity. So how do we connect these pieces? That's where services come in. Services provide a stable address for your unstable pods. There are three main types you need to know. ClusterIP. The default, it keeps traffic internal, only accessible inside the cluster. NodePort. It opens a specific port on every server so you can access it from outside. LoadBalancer. This integrates with your cloud provider like AWS and Azure to give you a real public IP address. Now let's talk about data. Containers are ephemeral, meaning when they die, their data dies with them. That's a problem for databases. To solve this, we use volumes. We have empty dir for temporary data that only lasts as long as the pod dies. Then we have the host path to read files directly from the server node. But for real application, we need something more robust. For permanent storage, Kubernetes uses a powerful abstraction called PV and PVC. Think of the persistent volume PV as the piece of actual hard drive storage provisioned by an admin. The persistent volume claim PVC is a ticket or request created by the user asking for the storage. Your application uses the PVC ticket to claim the PV storage. This separates the request for storage from the distinct physical infrastructure, making your apps portable and flexible. Finally, bringing it all together is the networking fabric. Kubernetes networking ensures communication at every level. Container Network Interface or CNI standardizes how networks are set up. Pod-to-pod communication allows direct communication across the nodes by assigning each pod its own IP. Service networking provides stable address and DNS names for pods which allows reliable communication within clusters. Ingress networking handles the outside world by providing HTTP routing and terminal for applications. This interconnected web is that what allows Kubernetes to be so resilient and scalable. As you can see, this diagram demonstrates how different pods and clusters connect with different networking equipment and form a network. Kubernetes is a vast ocean, but by understanding these core components, the control plane, the objects, the services, and the storage, you have the map to navigate it. Thank you for listening. I am happy to take questions. Hello and welcome. In this part, we are going to install and configure k0s, a lightweight Kubernetes distribution. First, we use curl to download the specific k0s binary release from GitHub. Once downloaded, we install the binary to our system path using sudo install command. Let's quickly verify the installation by checking the version. We are running version 1.34.2. Now we need to install the k0s controller. We use the single flag here. This tells k0s to run as a single node cluster, meaning this machine will act as both the controller and the worker node. Next, we start the k0s service. We can check the status to ensure controller is running. The API is proving successfully and workload are ready. Let's interact with the cluster using built-in kubectl. By running get nodes, we can see our machine Ubuntu 25 is listed, ready and acting as a control plane. Now let's deploy our first application. We use kubectl run to create a single pod running the NGINX image. To access the web server from outside, we need to expose it. We use the expose command to create a service named NGINX service on port 80, setting the type to NodePort. Let's find the assigned external port by getting the list of services. It looks like it is running on port 30172. Now let's check the pod status. NGINX is running. We can test this immediately in terminal using curl, and we see the HTML response. Let's also verify this in the web browser using server IP address and the specific port, which is 30172. And there it is. Welcome to NGINX. Next, let's try a database application. We will run a Redis port. I will use the watch command to monitor the status until the container is fully created and running. Now that it is running, let's execute command directly inside the container. We will use kubectl exec to enter the interactive mode and launch the Redis CLI. If we type ping, we get a pong response. The database is working perfectly. Let's exit the container. Let's deploy another web server, this time using Apache HTTPD. Just like before, we run the pod and then use the watch command to see the pod fully created and running. And then we expose it using a NodePort service. Checking the service list again, we see the HTTPD service is assigned to port 32708. Let's switch back to the browser. We enter the IP and the new port, which is 32708, and we see the it works message from Apache. Up until now, we have been running single pods. In real environment, we usually use deployments for better management. Here I am creating a deployment named mydep using the NGINX image, but this time I am specifying replicas equal 3. This will create 3 identical copies of the pod. We can verify the deployment was created successfully. Now let's expose this deployment as a service so we can access it. As you can see, the service is created in 31422 port. One of the best features of Kubernetes is scaling. We currently have 3 replicas. By running kubectl scale deployment, we can instantly increase this to 5 replicas. If we check the pods now, you can see original 3 are running and 2 new ones are also running. Total 5 pods are running now. Finally, let's demonstrate self-healing. I have 5 pods running. I am going to manually delete one of them. Let's copy the pod name and paste the pod name with kubectl delete. The pod is now deleted from the namespace. But watch what happens here. If we check again, as soon as the pod terminates, Kubernetes detects that we only have 4 pods instead of these are 5. It immediately creates a brand new pod to replace the deleted one, keeping our application stable and available. That's the power of Kubernetes. Thank you for watching. If you have any question, please feel free to ask.